Jai Hind. I am Ajay Dubey, Assistant Professor in Department of Mechanical Engineering, Ajay Kumar Garg Engineering College, Ghaziabad. The topic which I am going to discuss today is the column and strut, in which I will mainly focus upon column. And this is very important topic for mechanical engineering as well as civil engineering student point of view. And we all know the role and importance of column in structural engineering. We come across various instances of members under compression, and if the members under compression are kept in any position, these are known as strut. But when the members under compression are kept in vertical position, it is termed as column. Depending upon the slenderness ratio, that is the ratio of effective length of the column and least radius of gyration, columns are classified as short column, medium column and long column. Here we will see how the slenderness ratio varies for the different type of columns. The slenderness ratio L by K, if it is less than 32, it is the short column. If slenderness ratio rise between 32 to 120, it is medium column. And if slenderness ratio is greater than 120, it is long column. Now let us consider an axially loaded column. Say this is the column, loaded axially. As this load is increased gradually, a time will come when the column will fail, and this column will fail by crushing, because I have considered a short column here. Let us assume the crushing load BPC and stress induced is sigma c, and this stress is termed as crushing stress. Then we can find the crushing load PC, and this PC is sigma c into A, where A is the area of cross section of the column. By dividing the suitable factor of safety, we can find the safe load for the member under which it will not fail and it will work properly. But now members which we come across do not entirely fail by crushing. The length of these members are considerably more than its lateral dimensions, and the deflection starts, the buckling starts. These members, when axially loaded, force reaches a critical value, and once the member shows the sign of buckling, it will lead to the failure of the member. The load at which buckling just starts is termed as buckling load या critical load या crippling load, and the value of the critical load या buckling load is less than the crushing load. For long columns, crippling load is low, and for short column, crippling load is quite large. Now let us consider a column which deflects under load P like this. This is the load P. At any distance x, I am considering the deflection y of the column, and maximum deflection occurs at the mid portion of the column, and say this maximum deflection is E. So here we can find the extreme stress at the midsection of the column, and that extreme stress is P by A plus P into E by Z, where E is the maximum deflection and this occurs at the midsection. Say P by A is the direct stress, and this P into E by Z is the bending stress, and this bending stress occurs because of buckling produced by this load P. So here we can find the two stresses on the basis of this equation. Say this is sigma. So here if I consider the plus sign, positive sign, I will find sigma max, and that is sigma naught plus sigma b, and sigma min equal to sigma naught minus sigma b. Now once this sigma max reaches the crushing stress of the column material, the member will fail. So here it is to be noted that the failure of the material, yes, failure of the member is not just because of sigma b, it is also because of the combined effect of sigma naught and sigma b. Now come to the Euler's theory, and this Euler's theory is for the very long columns. Here certain assumptions has been made by the Euler's for the long columns, and what are those assumptions? The column is initially straight, the column's cross section is uniform throughout, the line of thrust coincides exactly with the axis of the column, the material is homogeneous and isotropic, the shortening of column due to axial compression is negligible. It is very important to note the shortening of the column due to axial compression is negligible. It means once we are applying this compressive load over the column, so the length of column will not decrease. If it happens, it is negligible. So what actually happens? Under the compression load, column buckles. This is the buckling. Now there are 4 different cases of buckling of the column, and those 4 cases are both ends hinged. When the both ends of the column are hinged, then what is the buckling load या crippling load या critical load? Second, when one end fixed and other free, then what is the crippling load? Both end fixed, then what is the crippling load? And one end fixed and other hinge, then what is the crippling load? So it is very important to calculate the value of crippling load, because on the basis of that we can find what load should be applied on the column to avoid the buckling. If any load above the crippling load is applied on the column, it will buckle and ultimately it will lead towards the failure of the column. But if it is less than that, it is safe and it will not fail at all. Here now I will consider both end hinged. Both end hinged. So consider a long column. This is the long column. This is, and both ends are hinged here. Both ends are hinged. It is subjected to axial compressive load P. Now, from bottom point of the column at any distance x, lateral deflection of the column has been taken as y. Now I can find the bending moment at this position. And what is the bending moment at this position? We'll see. So writing the differential equation of bending, and that is EI d2y upon dx square, and that is equal to m, where m is the bending moment. Now how will we consider the sign of bending moment, whether positive or negative? Very easy to understand. If the curvature of the column is like this, means this is concavity towards the initial center line of the column. If a bending moment produces a concavity towards the initial center line of the member, bending moment is considered as negative. And if the bending moment produces convexity towards the initial center line of the member, it is considered as positive. So how that convexity looks like? It looks like this. This is. If you are applying a load and column buckles like this, so this is the convexity towards the initial center line of the column. Here bending moment will be considered as positive, and here bending moment is considered as negative. Now we'll write the value of bending moment here, and that is negative minus P into y, because there is a concavity towards the initial center line of the member. Now rearranging the equation, EI d2y by dx square plus py equal to 0. Dividing by EI, it will reduce d2y by dx square plus p by ei into y equal to 0. Now let us consider this p upon ei as a alpha square. Equation will become as d2y by dx square plus alpha square y equal to 0. This is the differential equation. Now we can find the general solution of this differential equation for deflection. Is y equal to a sine alpha x plus b cos alpha x. Now a and b are the coefficients, the constants. We can find the value of a and b by putting different boundary conditions. And what is that boundary condition? If I see, both in hinge x. If you see, since x is varying from bottom side, if x equal to 0, if x equal to 0, y is 0, because at this end there is no deflection. Again, at x equal to L, and what is L? L is nothing but the initial length of the column, that is L. So when x equal to L, again deflection at this end is, upper end is 0, y equal to 0. So just by putting the first boundary condition, we see that value of b comes out as 0. Putting the first boundary condition, 0 equal to a sine alpha into 0 plus b cos alpha into 0. So this becomes 0 plus b into cos 0 is 1. So this shows b equal to 0. Similarly, we can find the value of a as well. So putting the second boundary condition, we can find the value of a at x equal to L, y is 0. 0 equal to a sine alpha L plus b cos alpha L, and here we got b as 0, that's why this is going to be 0. Here from this we see that a sine alpha L equal to 0. So if product of a and sine alpha L equal to 0, so what is the chance? Either a is 0 or sine alpha L is 0. But if a is 0 here, then deflection is 0 for all values of load. And if deflection is 0 for all values of load, means there is no bending, there is no buckling. Now then we'll avoid that situation. Now we'll consider sine alpha L equal to 0. If it is the case, then we can see alpha L equal to either 0 or pi or 2 pi or 3 pi, and so on, n pi. So considering least practical value, here alpha L equal to pi, and we all know alpha L, and that alpha L is root P upon Ei into L equal to pi. Now squaring both sides. From here, squaring both sides. P by Ei into L square equal to pi square. Therefore, P equal to pi square Ei upon L square. The P which I have just computed is the crippling load, and it is the load at which the column will just start buckling or bending. Here L is the effective length of the column. In the case of both hinge, effective length is nothing but the length of the column. Ei is the flexural rigidity. I considered here is the least moment of inertia, which depends upon the cross section. So there are two moments of inertia. Out of those two moments of inertia, if one is more and one is less, then we will consider the least moment of inertia. So this is the crippling load, E crippling, that is pi square Ei upon L square. Next cases I will discuss in the next video. Thank you very much.